This video is covering section 7.2b, the disk and washer methods. 7.2a was talking about finding the volume of solids with known cross-sections. So as we had a flat base, and then we built off of that base triangles, squares, semicircles, things like that. So now with the disk and washer methods, it's a method of finding the volume of solids of revolution. So what our cross-sections now are actually going to be like disks or circles. Okay, so that's going to be our cross section. So with this known cross sections of flat bases, we had semicircles. So we had to cut that circle in half. But now we're actually going to be adding up a bunch of circles. So what you can think of, if you look at this vase here, this is a solid of revolution. So if I take like this axis of revolution down the middle, and you can kind of think of this, let's think of this as like on a coordinate plane. I don't know, I'll put it somewhere here. And so let's pretend that I had some function that looked like that, the outline of the vase. And then I were to revolve that around the y-axis. Then you would have different sections like this. So when I were to revolve them, you would get these circles, and the whole thing would form that vase. Okay, so with solids of revolution, we have the axis of revolution. So that could be the x-axis, the y-axis, or any other horizontal or vertical line. In this class, we're not getting to oblique axis of revolutions. So the simplest such solid for doing a solid of revolution is just a simple disk. So that is, if I were to take just a regular rectangle and revolve it around, let's say, the x-axis, then you would get this disk shape here. Okay, so if I were to find the volume of this disk, you can do that without calculus, because really what the disk is it's a flattened cylinder. So the area of a cylinder is area of the base times the height. So the area of that base is a circle, and we're calling our r is our radius, big R. So the area of a circle is pi r squared, and then times our height, and our height here is just that little bitty width. So I'm going to say that's times W. Now, if I had a bunch of these disks, so looking over here at the vase, if I had a bunch of these disks and I wanted to find now the volume of that vase, I could add up several disks, right? And ultimately, we would want that width to be infinitesimally small. So then what happens is we have an integral to add up all of those disks. Pi is a constant, so we're going to pull pi outside. So when I sum up a bunch of disks, that's an integral. And then r would be our function boundary squared, and then our width, we want that to become infinitesimally small, so that is going to be like dw. So this right here is the formula for finding the volume of a solid of revolution. We can take with respect to x, or we can take with respect to y. So the base that I had, that would be taken with respect to y, because we would have horizontal representative rectangles there. And so just skipping down to this box here, this is going to be what is going to be mostly important. So for horizontal axis of revolution, so that would be like the x-axis, everything would be in terms of x. Because I think it says down here in the note, your representative rectangle needs to be perpendicular to the axis of revolution. So if my axis of revolution is the x-axis, then my rectangle needs to be a vertical rectangle. So horizontal axis of revolution, you're taking with respect to x. And then a vertical axis of revolution, my rectangles are going to be horizontal. So then I would be taking with respect to y. Okay? So let's just see how this looks in a problem. So we want to find the volume of the solid formed by revolving the region bounded by the graph of square root of sine x and the x-axis from 0 to pi about the x-axis. So when they say about the x-axis, they're telling us that's the axis of revolution. All right, so if our axis of revolution is horizontal, then we want to find everything with respect to x. We want vertical rectangles. So first of all, we're going to find the graph of the square root of sine x, which you could use your calculator if you need to, but I'm just going to give it to you. It looks almost just like actually the sine of x from 0 to pi. just kind of that curve there, which I'm going to highlight to show that that's the region that I started off with. So that's the region bounded by that curve. All right, so what we're going to do is we're going to take that yellow two-dimensional shape, and we're now going to rotate it around the x-axis. So I like to show a little circle there, arrow, to show which axis I'm rotating around. All right, then what I like to do is I like to visualize this. So if I rotate this figure around the x-axis, you're going to get a three-dimensional shape. It's going to come down to -1, and it's going to look something like that. Now, just like when we found the area between two curves, I want you to draw a representative rectangle. So I'm going to do that here. So if I were to just draw that one representative rectangle rotated around that x-axis, then you're going to get this circle. So that is, if I split that figure apart, you see a circle. All right, so it looks kind of like an acorn, or some of you may think Pokemon or something like that. That's kind of what this looks like, this three-dimensional shape that you get. So now we want to calculate the volume of that full shape. And like I said, in class, we are going to look more kind of at hands-on feel, and also kind of graphical representations that look better than my drawings. All right, so to find the volume here, this is vertical rectangles. So I'm going to look at this formula here. So I need to figure out what that R is. And R for this problem is kind of like the S that we had in the previous problems. So this length is what I'm going to call my R. That's my radius. So that's bounded by the curve of square root of sine on the top, and on the bottom is just the x-axis. So R is just the square root of sine x. So my volume is going to be pi times the integral from 0 to pi, because we have from left to right there, of big R square root of sine x squared, and then with respect to x. So if I clean that up, you would actually get pi times 0, integral from 0 to pi of sine x dx. And if you were to solve all of that out, you would get 2 pi. And if we were talking about units here, this would be units cubed, because you're finding a volume. So just to recap, I just want to make sure that when you're thinking of solid of revolution, I want you to think of adding up a bunch of circles. So the area of a circle is pi r squared. And then the integral is adding up a bunch of, and then to get volume, that's that dx piece, which is giving you kind of the width, which is giving you a three-dimensional cubic function. For number 2, I'm going to quickly just pause and draw the picture really quickly, and then we'll calculate the volume. Okay, so here's my picture. I have 2 minus x squared, and that's bounded by the line y equals 1, and then we're going to rotate around the line y equals 1 as well. So you're going to have something like this. So when we rotate it, it'll look almost just like the other figure. So we have this like Pokemon shape again. So it looks very similar. All right, so to find the volume, though, it's a little bit different because my axis of revolution has been moved. So we have to take that into consideration. So think now that this is my R. So instead of being bound by one curve, this is actually bound by 2 different curves. Because if you look at the top, that's 2 minus x squared, and then minus the bottom is the function y equals 1. So that is something that changes. So then that whole R would be 1 minus x squared. So then to find the volume, the formula is pi r squared, so pi times the integral from, now you're looking at the yellow region to tell your limits of integration. So that would be from -1 to 1. And then of r, so 1 minus x squared dx. So for now, we're just going to be worried about finding the integral setup, not so much the answer at this point. Okay, so just a reminder again, the reason why I did with respect to x is because I had a y equals 1 is a horizontal axis of revolution. And so if I have a horizontal axis of revolution, I take vertical cross sections, which means with respect to x. Okay, so now we have the washer method. So think of the disk as solid. So those are solid circles. There's no holes in those circles. So sometimes when we revolve figures, you're going to have gaps. And that's when we're going to use the washer method. So think of a washer. It's kind of the little piece that goes in between like a bolt. So it's a circle and then with a concentric circle inside. So instead of adding up a bunch of circles, I'm adding up a bunch of washers like this. So we're going to find the volume of this washer. So again, it has that width, but let's talk about the area of just this figure that I have here. So you have two radiuses. You have the big radius, and I'm going to call that big R, which is actually the same R as the R with the disk method. And then you have to cut out this little r, this little radius, so I'm going to call that little r. So if I was to find the area of that figure, you would have to find the area of the outer circle and then subtract the area of the inner circle. So the area of that would be, area of the outer would be pi r squared with the big R minus pi little r squared. And then, of course, the pi's in common, so you can take that out. One thing that I want to make sure you don't make the mistake of is saying big R minus little r and then that squared. That is absolutely incorrect, so make sure you don't make that mistake. All right, so the volume of that washer, if I was to find the volume of like a single washer like this, then you would have the area of the base times the height. So the area of the base is pi times r squared minus r squared, then times that certain width. So again, if I were to add all of those up, infinitesimally small washers, this would be pi times the integral of r squared minus r squared, and then, of course, dw. Okay, so we have the same thing with the washer method as we had with the disk method. So here's our formula that you are going to need to memorize. Now, this is only in terms of x, but the same thing applies with in terms of y. So I have kind of a different picture here. So here's my this little moon-shaped base here. And then I'm revolving around this. So you see you have this huge gap in between. So if I took this representative rectangle and I rotated around that, you're going to get some kind of shape down here. And I know they draw it out for me, but I want to show you kind of this washer here that I like to draw. So this is going to come all the way down here. So we have that circle, but then that big circle has a gap in between it. So what I'm doing, what I kind of drew there, if I kind of flatten it out, is a washer. Okay, and so what you have to decide and figure out is what's the big R and what's the little r, and we're going to take time to figure that out. Okay? And actually, before we move on, I want to take this picture. So I erased what I just drew, but I want to make sure we know how to find big R and little r from this picture before we move on, because it can be kind of confusing for some people. So big R, our radii are always going to start on the axis of revolution. Okay, so you see I have big R and then I have little r, and I'm gonna make little r. I'm gonna put it as this length, and there's big R. Okay, so I have two radii. So I've got those two red lines there. So big R, I'm always going to start at the axis of revolution on this line, and I'm going to go up until I reach the very outer function, which is up there. So that red bar there is my big R. Okay, now if I were to find the little r, which I'll do in a different color, remember my radius is always going to start from the axis of revolution. And then it's going to go up, and it's going to stop when I hit the first function. So you can see my red is bigger than the green. So again, you start from the axis of revolution and go out until you hit the outer function, that's big R. Go out until you hit the smaller function, that's little r. So hopefully that'll be helpful for you guys. So let's try example 3. So find the volume of the solid formed by revolving the graphs bounded by the square root of x and x squared and the x-axis. Now notice that they don't specify whether you're going to use disk or washer. That's going to have to be up to you. Now you know that you're using solid of revolution because it says revolve the region. We're revolving about the x-axis, which is horizontal, so that means we're going to take vertical cross-sections. Everything's in terms of x. So really quickly, I'm going to do a sketch. If I did this, square root of x and x squared, square root of x is going to look like this, x squared will look like this, and they meet at the point 1, 1. All right, so that's my figure, which I'm going to highlight. looks kind of like a banana. So I'm going to take vertical cross sections, and then that's going to be revolved around the x-axis. So you're going to end up getting a figure that looks something like that. Now, and so you're going to rotate it, and it kind of looks like maybe a flower or something, or a clamshell. So what I want to find, or first of all, you need to decide, are you going to do disc or washer? Now, disc, when you rotate this around, you're going to have no gaps at all. See how there's this whole gap, this white space right in here between the region and the axis of revolution. If there's any kind of gap between the region and the axis of revolution, then you're going to do washer. Okay, because what happens when I rotate that around, you're going to have this inner circle that you're going to have to take off. Okay, so now I'm going to take that semicircle away so that we can easily see this drawing a little bit better. So what I'm going to do is I'm going to draw, let's do a red, like I did in the first one, to find the big R and the little r. So we're always going to start with the axis of revolution, which here is on the x-axis. And I'm going to go out until I hit my outer region. So here. So that is my big R length. And then in a different color, I'll do my little r. So again, it doesn't matter where. I'm just going to do it here. Start on axis of revolution, go out, hit my first function, and that is little r. So to find big R and little r, those are vertical lengths. So to find those lengths, you find top minus bottom. So big R, the top that this top right here hits, is the function square root of x. And then the bottom, which is the axis of revolution, is just 0. So I don't have to write that down. Then little r, the top function, is here. And that is x squared. And again, the bottom function is 0. All right, so that's how you find big R and little r. If you change your axis of revolution, then that gets a little bit different, which we'll get to. So now this would be the volume by washer method, would be pi times the integral from 0 to 1 of big R squared, which is square root of x squared, minus little r squared dx. Okay, and again, we're just focusing on writing the integrals now, not solving today. Okay, I'm going to do one final example in this video, and then the rest we're going to do in class. So this one, we have the region bounded by x squared plus 1, y equals 0, x equals 0, that is the x and y axis, and the line x equals 0. Now this one's different because we are going to rotate about the y axis. So that means we're going to take horizontal cross sections. So since the y axis is vertical, that means horizontal cross sections. In other words, everything is going to be in terms of y. Okay. All right, so let's graph this really quickly. X squared plus 1 bounded by the x-axis, y-axis, and x equals 1. So we'll have something that looks like that. Okay, and I'll highlight. Okay, so if I were to revolve this around the y-axis, and remember I want horizontal cross sections because they're perpendicular to the y-axis. And I revolve this shape around, you'll get something that looks like that. Okay, so if you look down here where I've drawn my rectangle, my representative rectangle, and I rotate that around, then what method is that? There's no gaps at all. So that would be disc method. However, you might see a problem if I put my representative rectangle here and I rotate it around. I've got a huge gap, and that's going to be washer method. Okay, so what I actually have to do here is split this up into two regions. So I have the bottom portion of this and the top portion of this. So the bottom I'm going to have to do disc method, and the top I'm going to have to do washer method. All right, and sometimes you're going to have to do that. But if you look at the bottom, actually, that's just a regular cylinder. And you could do the calculus behind it. But since that's just a regular cylinder, we can just find the area of that like normal, which is totally fine and is acceptable. So the bottom is just a regular cylinder. And I'm writing too fast, so I'm messing up. This is a regular cylinder. So the formula for the volume of a regular cylinder is just area of the base times the height, or pi r squared times the height. And we know that has a radius of 1 and also a height of 1. So this would be just simply pi for the bottom portion. Okay. So then we need to calculate the top. Now, since everything we want horizontal cross sections, we need everything in terms of y. So that is this equation up here. I need to put that in terms of y. So that is I need to solve for x. So that's going to be x equals the positive and negative square root of y minus 1. Okay. So now since it's washer method, we need to figure out big R and little r. So I'm just going to quickly redraw this since my first one was kind of messy. So we're taking this, revolving it around. Oh, that's not what I meant to do, sorry. There we go. Okay. So if you want to find your big R, so that would be from my axis of revolution all the way out to my outermost function. So that is big R. Then to find little r, axis of revolution, to first function. So that's little r. Okay. So big R, since we're doing with respect to y, is right minus left. So big R, the right function is just 1 and will always be 1 the whole time. Okay? And then minus 0, of course. And then the smaller function is bounded by that parabola, which is the positive we found from up here, square root of y minus 1. Okay, so that's big R and little r for the top portion. And just also note that we are going from 1 to 2 on the y values. All right, so the top portion is going to be pi times the integral from 1 to 2 of big R squared minus little r squared dy. And if you were to solve that out, which is not too bad, you would get pi over 2, which makes sense that it would be smaller than the bottom portion. So then to get your total, you would add those two together, giving you 3 pi over 2. Okay, so that is disk and washer method.